In this video, we're going to take a look at the ratio test and the root test. Now, this is where we start to get into more complicated series where there's lots of different types of going on. So not all series are really easy to integrate. So the integral test isn't going to work for a series like this one, because it's going to be very hard to integrate, especially with that n factorial in it. Also, in this series, it's not really easy to compare it, or at least to see a comparison, at least not directly right now. So what we want is a non-dependent convergence test, meaning not dependent on being able to integrate, not dependent upon being able to compare to some other series that I know. Well, the good news is we're going to have a couple of tests to use. The bad news is that each of these tests is going to give us three options. One option is going to conclude that the series converges. And not only will it converge, it will converge absolutely. You don't need to know what that word converge absolutely is versus converge. It just means converge. Absolutely, we'll go over that in another video. The second option that we have is that our series may diverge. But then we have this third option where the test is inconclusive. So the test tells us we don't know about this one. So each of these new tests, one of them will be the ratio test, one of them will be the root test, will have three conclusions. We can conclude that the series converges absolutely. We can conclude that the series diverges, or we'll have an inconclusive or an unknown option. Again, converge absolutely does have a specific meaning. We'll take a look at that in another video. Let's look at the first test. The first test that we're going to look at is called the ratio test. Now, I left off the n equals 1 to infinity, but if you ever see this sum, assume it's an infinite summation. So the ratio test for an infinite series says that the infinite series converges absolutely if the limit of the ratio of the terms of that series as n goes to infinity is less than 1. The series diverges if the limit of that ratio of the terms of the series is greater than 1. And the ratio test is inconclusive if the limit of the terms of the series is equal to 1. Now, the terms are always going to be an absolute value. Most of the time we will be dealing with positive terms, but we could have some negative terms, so that's why they use those absolute values. So the limit of term a sub n plus 1 divided by a sub n, if it's less than 1, then the series converges absolutely. If it's greater than 1, then the series diverges. And if that is equal to 1, then we're in the inconclusive scenario. So if we can calculate this limit, then we can use the ratio test. So let's do that. Let's take the infinite series n factorial divided by 3 to the nth power, summed up from n equals 1 to infinity. And we'll take a look at this series in terms of the ratio test. So in terms of the ratio test, I need to calculate this limit. And we'll see that once we see what the ratio test is actually doing, that limit calculation we can kind of skip. But for right now, let's calculate this limit. Now you have to put the a sub n plus 1 term on the top and the a sub n term on the bottom. The nth term is n factorial over 3 to the n. The n plus 1 term is going to be a ratio where I take n plus 1 factorial divided by 3 to the n plus 1 power. Now, as usual, when I'm dividing fractions, what I can do is I can multiply by the reciprocal of the fraction I'm dividing. If I do that, I'm going to get 3 to the nth power multiplied times n plus 1 factorial on top. And on bottom, I'm going to get 3 to the n plus 1 power multiplied times n factorial. Again, that's my bottom. Now, a couple of things. 3 to the n plus 1. Let me actually copy this. 3 to the n plus 1 is like 3 to the n times an extra copy of 3. N plus 1 factorial. Remember what factorial does. It takes every number and then multiplies every positive integer. So if we have something like 7 factorial, we'd get 7 times 6 times 5 times 4 times 3 times 2 times 1. Or if I wanted to rewrite that, I could say 7 factorial is actually 7 times 6 times 5 times 4 times 3 times 2 times 1 is just 6 factorial. So n plus 1 factorial is the same as n plus 1 times n factorial. And now lots of things cancel out. So now I can see that the n factorial on top cancels out with the n factorial on bottom. 3 to the nth power cancels out with this 3 to the nth power. And I would just be left with n plus 1 as a number divided by the number 3. So doing the algebra shows me that this limit is actually infinity because n plus 1 is going to grow and 3 is just going to stay still. Now, obviously, that's bigger than 1. Because that's bigger than 1, infinity is bigger than 1, the ratio test says, therefore, this series, the original series we were talking about, has to diverge. So that series, I know by the ratio test, diverges. Now, I did this manually where I computed this limit. Oftentimes, I do what I would consider an informal ratio test where I don't have to compute the limit. So what do I mean by that? Well, what I mean by this is oftentimes when I'm given an infinite series, I'm given an infinite series where the types of growth are different. In this case, n factorial is factorial growth. Three to the n is exponential growth. And I can ask myself, which one of these is faster? Well, it turns out that factorial growth is faster type growth. It's a growth of a faster order, we say in mathematics, than exponential growth. Since the faster growth of each of these terms, the faster order of growth is on top, that means my terms are going to grow out to infinity with high values of n. Now, you might not be convinced that factorial growth is faster than exponential growth, but just follow along again the idea of factorial. 3 to the n, as n increases, we're multiplying by 3 and 3 and 3 and another 3. Well, as n increases here, for the first few numbers, we're multiplying by 1, 2, and 3. That's numbers that are less than 3. But after n gets above 4, now we're multiplying this number by 4, and then 5, and then 6, and then 7, and then 8, and then 9. And all of those numbers are going to be bigger than 3. So repeated multiplication by 3 is not going to grow as fast as repeated multiplication by a growing number. Hopefully that makes sense. You could, if you wanted to, create a table to show that. In fact, let me go ahead and do that right now. So we'll look at n factorial, whoops, versus 3 to the nth power. So when n is equal to 1, I just get 1. When n is equal to 1, I get 3. And this is how I'm going to show this. When n is equal to 2, I get 1 times 2, which is 2. When n is equal to 2, I get 3 times 3, which obviously is 9. So the first few terms, when I multiply, when I increase n, it's not growing as fast. Let's say n is equal to 3. Then I end up with 1 times 2 times 3, which is obviously 6. Over here, I'd get 3 times 3 times 3, which is 27. Now notice that going from 2 to 6 is a multiplication by 3. 9 to 27 is a multiplication by 3. So we're actually kind of growing at the same rate. in that one step. And now in the next few steps, the factorial will be growing by more. So 1 times 2 times 3 times 4 is going to give me 24. 3 to the fourth is 3 times 3 times 3 times 3. I'm just going to write 3 to the fourth, but we're multiplying by another copy of 3. Actually, no, I changed my mind. So while 3 to the n is still bigger, they actually got, this one grew by a factor of 4. This one only grew by a factor of 3. And then we can do the exact same thing a few more times. Let's do 5. I'm just going to write 5 factorial here. So 5 factorial was 120. And then that's 3 to the fifth. On the left, I'm multiplying by 5. On the right, I'm multiplying by 3. That's 243. And then I multiply by 6 to get 6 factorial. 120 times 6 is 720. We've actually seen that before. 3 to the 6th power is 243 times another 3. So that's 729. And then with 7 factorial, finally the factorial overtakes this 3 to the n. We get 5,040 with the factorial when I plug in 7. And then 3 to the 7th becomes 2,187. And from here on out, when I increase the values for the factorial, I'll be multiplying by bigger numbers than 3. So from here on out, the factorial is just going to grow way, way faster. So in factorial is faster growth than an exponential function. Now, that being said, I know that was kind of a long aside. That being said, this means that my terms are getting really, really big because the n factorial is in the top. So for large values of n, these terms just keep growing and growing and growing. And therefore, it's pretty obvious that the infinite series, when I add them up, is going to have to diverge. That's what I mean by an informal version of the ratio test. And that's really what a ratio test is good at. We can calculate this limit if we want to, but what the ratio test is really good at is comparing different types of growth. And by different types, I mean different orders of growth. So what I'm talking about here is things like faster growth versus slower growth. N to the n turns out to grow even faster than n factorial. N factorial is faster growth than an exponential function whose base is bigger than 1. An exponential function is a faster order of growth than n to a power, where the power is bigger than 0. We don't want to have negatives. That would be a decay. And then n to any power is going to be faster growth than the natural log of n. And then any constant is actually going to be no growth at all. And so natural log grows faster than standing still. N to a power grows faster than natural log. Exponential grows faster than n to a power. Factorial, we just saw, grows faster than exponential. And n to the n grows faster than factorial. And you could do all kinds of other combinations of these things. But if I look at the ratio test and I have a bunch of different types of growth, then the fastest order of growth is going to dictate what that infinite series does. If I have n factorial and some other slower growths, then these other slower growths are basically kind of like standing still compared to the n factorial, at least when n gets really big. And therefore, I can take like my example one on top and I say, well, this series has two different orders of growth. It has factorial and exponential. Factorial is the greater growth. So what this series is going to do is the same as an infinite sum of n factorial over, and I can ignore the other types of growth. It's like n factorial over 1, which obviously diverges. So that's the informal way of looking at the ratio test and what the ratio test is doing. It's looking for fastest order of growth. So let's take a look at this example with that in mind. So we are going to determine the convergence of this series using the ratio test. And again, I am going to use the informal version of that ratio test. So in this case, I have two types of growth. I have an n squared growth versus 5 to the n. This is n squared is like an n to a power type growth. I often call this polynomial growth because if the power is a positive integer, then we get a polynomial. But like 2, this is polynomial. Technically, it doesn't always have to be a whole number. But this is n to the p growth versus 5 to the n is exponential growth. This one is the faster order of growth. So that means this infinite series is going to behave in the same way. It's not the same, but it's going to behave the same as if the n to the p growth wasn't around. It's going to behave the exact same as this. And this series, this one on the right, is geometric with a r of 1/5. So we know that converges. Another way to say that is that the faster growth is in the denominator. The faster order of growth is in the denominator. So my fractions are going to go to 0 very quickly, and therefore the entire infinite series converges. So that's another way to say that. Faster order of growth is in the denominator. So it's going to behave like 1 over 5 to the n. Again, these terms are going to go to 0 very quickly. And therefore, my series is going to converge. Hopefully that makes sense. Now, if you want, you can, in fact, utilize the actual limit of the ratio of a sub n plus 1 over a sub n. I typically don't. I typically just do this, and I won't even write this step. I'll just say, oh yeah, faster growth is in the denominator, therefore it dictates everything. Um, but there are some instructors who may ask for a calculation of that limit. In this case, I'll go ahead and do it, but I won't in the next few cases. So a sub n, the nth term in my infinite series is n squared divided by 5 to the n. A sub n plus 1 is going to be n plus 1 quantity squared divided by 5 to the n plus 1. N plus 1 in the exponent. And then when I multiply by the reciprocal of that fraction in the denominator, I get a limit of, well, we'd have n plus 1 squared on the top and 5 to the n on the top. On the bottom, I'd have 5 to the n plus 1 multiplied times an n squared. I'm going to do kind of 2 steps here. The first step is I will expand n plus 1 squared. If I expand n plus 1 squared, I'm going to get n squared plus 2n plus 1. Notice that the real key there is that we have an n squared. And then on the bottom, 5 to the n plus 1 is 5 to the n times an extra copy of 5. And all of a sudden, this 5 to the n and that 5 to the n will cancel out. Notice that top, bottom, both of those are polynomials of degree 2. So I just have to state what the coefficient is on the top over the coefficient on the bottom of the n squared term. So we get 1/5, which is obviously less than 1, which tells us that our infinite series converges, and technically tells us that our infinite series converges absolutely. So if you had to calculate that limit, you absolutely could, and that tells us that our series converges absolutely. I like the informal way of talking about this a lot more than the limit calculation. So that's what I do. I say, what's the fastest growth here? the fastest order of growth is going to overpower everything else. And therefore, if the fastest order of growth is sort of in the denominator, then these terms are going to go to zero really fast. If, like in this case, the fastest order of growth was in the numerator, then the terms are going to go off to infinity. Let's look at another example. Let's determine the convergence of this series using the ratio test. And since the ratio test goes pretty quickly with this one, you can also try to do this next one as well. I'll do both of these. We have in example 3, an n factorial divided by n to the nth power, and then an n to the third times 4 to the nth power divided by n factorial, summed up from 1 to infinity. That's the fourth example. If you want to try both of these on your own, you can. In a couple of seconds, I will do both of these again in the informal way of doing these ratio tests. So infinite series, sum of n factorial divided by n to the n. Infinite series, infinite sum of n to the third divided by 4 to the nth power divided by n factorial. Excuse me, n to the third times 4 to the nth power divided by n factorial. All right, so here we have a couple of types of growth going on in this problem. In the numerator, we have an n factorial growth. That is, again, factorial type growth. That's happening in the numerator. And then we have an n to the nth power growth. N to nth power growth. That's happening in the denominator. Again, you can convince yourself if you want to draw a table that of which one is a faster growth. It's pretty obvious though here when I do a 7 factorial, I'm doing 7 times 6 times 5 times 4 times 3 times 2 times 1. Here we're doing 7 times 7 times 7 times 7. So since the 7 times 6 is going to be always smaller than 7 times 7, and 8 times 7 times 6 is going to be smaller than 8 times 8 times 8. The nth to the nth power growth is going to be the faster one. That's in the denominator. So therefore, these terms individually are going to go to zero pretty quick. And when I sum them up, this infinite series is going to have to converge. Now, I'm arguing that they're going to zero really quickly, these terms. And specifically, I'm really arguing that they're going to zero quicker than something like 1 over n squared. Remember, if I took the infinite series 1 over n squared, we saw that converges. N to the nth type growth is much faster than n to the p type growth. And even if I throw in, I'm counteracting that with some other orders of growth, it's still a lot faster than n to the p growth, and therefore it's going to go to zero. The terms are going to go to zero even faster than 1 over n squared. Hopefully that makes sense. Okay, so it's not just that these go to zero, these go to zero really fast. Here I have a lot of different types of growth. I have an n to the third type growth. That's n to the p growth. I have 4 to the n. That's exponential growth. And then I have n factorial. That's obviously factorial growth. This factorial growth is the fastest. Now, does it matter that there's two different types of growth being multiplied on top? It turns out no. The factorial will dominate that as long as n gets really, really big. So when n gets really, really big, the factorial is going to take over. And so this thing is going to behave in a way similar to like 1 over n factorial. Okay, so even if I have multiple different types of growth here, an exponential times an n to the p, the product of those things doesn't actually overcome the factorial growth. So that's something you can convince yourself of if you want, but it is true. So I will just go with it. So of all of the types of growth, the factorial is the fastest. The multiplication of exponential times n to the p doesn't actually overcome factorial growth. And therefore, this infinite series converges. Fastest type of growth is in the denominator, so the infinite series converges. So this is sort of the informal way of doing the ratio test, just looking for the fastest growth around, convincing yourself that when you have a product of exponential times n to the p, that still doesn't overcome our factorial. Convincing yourself that n to the n power is a faster growth than factorial growth. And then once we see that, obviously we can determine, is the faster growth in the numerator, is the faster growth in the denominator. If it's in the denominator, then the terms are going to go to zero very quickly. If it's in the numerator, then the terms are going to go off to infinity. Now, once you do this, it in the informal sense, then some of the infinite series go really, really quick. Like this one in example 5, we have 2n factorial on top and n to the third plus 6n squared minus 9n plus 12 on bottom. Using the informal version of the ratio test, I just say, well, 2n factorial is going to grow way, way faster than a polynomial will grow. The polynomial is like n to the p growth. 2n factorial is factorial growth. and therefore the top is growing faster. Therefore, the terms are going to grow to infinity. And then therefore, this infinite series is going to sum up to infinity or diverge. So the ratio test goes really, really quickly, the informal ratio test, on something like this. We just say faster growth in the numerator than in the denominator. So my terms go off to infinity. So the infinite series has to diverge. I'll write that down. So all we say is that the faster growth order here is the top, the numerator of 2n factorial, and therefore this infinite sum has to diverge. Okay. By the way, bottom is a polynomial. That's an n to the p type growth. So it's factorial versus n to the p. Factorial is going to, again, I informally use the word dominate, meaning that everything else is going to look like it's standing still in comparison. It's like me running and then a jet plane flies right by me. Well, as I'm running, I'm going to look like I'm standing still compared to an airplane flying by. Well, that's the same thing. This denominator looks like it's standing still compared to this numerator when n gets really, really big. So factorial growth is faster. It's in the numerator. The infinite series diverges. Here, factorial growth in the denominator, that's faster growth than even the product of these two. So denominator has faster growth, therefore the infinite series converges. In this one, we're just comparing 1 and 1. Denominator has faster growth, so converges. Now, one thing to be wary of in the ratio test is something like this. If I have n squared over, n squared plus 3n over n to the fourth plus 8, I cannot simply say that the denominator is a faster growth because both the denominator and the numerator are n to the p type growth. So both denominator and numerator are the same order of growth. And in this case, that forces me to use a different type of test. Now, we've done stuff like this before. So we can use a different type of test. We can use a limit comparison test, for instance, to determine whether this converges or diverges. But the ratio test on this one is coming up inconclusive because they're the same order of growth. Even though there are different exponents in the numerator and denominator, even though I could use the limit comparison test to determine the convergence here, the ratio test would be inconclusive. Okay? And if I did actually calculate that limit of a sub n plus 1 divided by a sub n, it turns out, I won't go through the calculations, it turns out this is the case or this is a case where the limit would have come up as a 1. So in other words, again, I'm sparing the hard work here, but if you looked at the limit of this ratio, it would, and you did the hard work of calculating it, it would come out as 1, and therefore the ratio test would be inconclusive. And that's the case with any polynomial over polynomial. If I had n to the 11th plus 3 to the times n divided by n to the 4th plus n, it would still come out as 1. Anytime I have polynomial growth or n to the p growth over another n to the p growth, that's the type of scenario where the ratio test is inconclusive. And we'd have to use a different test. And lucky for us, we do have a different test that could work here. So while the ratio test is inconclusive, you could do a limit comparison test. And I'll just, that one we saw in our previous video. And we could compare this to 1 over n squared, which we know converges because that's a p-series. And so that means our summation also converges. Our infinite series also converges through the limit comparison test. But again, the ratio test would have been inconclusive. Hopefully that all makes sense. So when we talk about faster order of growth, we mean growths of different types, like exponential versus factorial, n to the p versus exponential, natural log of n versus n to the p, that type of thing. So the ratio test doesn't work well when both numerator and denominator are n to the p type functions. By the way, even if I threw a natural log in here, like a natural log of n, if my fastest growth around is n to the p, so let's go back to that. If my fastest growth is n to the p, then I probably want to utilize a different test. Ratio tests work really well when the fastest growth around is something like n to the n, or a factorial growth, or an exponential growth. But with n to the p as my fastest growth around, or natural log, then the ratio test isn't very good. The informal way, I should say, of the ratio test. So be careful about that. Again, really good if our fastest growth is like exponential, factorial, n to the n. Not really good if our fastest growth around is n to the p growth or natural log of n growth. That's where we get the inconclusive. So there you go. So ratio test is inconclusive when we have this, but again, we can, if we do have that, we have other tests that we've seen before. The other test that we're going to look at in this section is the root test. The root test says an infinite series converges absolutely if limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. The infinite series diverges if the limit of that nth root is greater than 1. And once again, the root test is inconclusive if the limit as n goes to infinity of the nth root is equal to 1. So again, we have absolute convergence, divergence, or inconclusive. Now, taking the nth root of the absolute value, again, we have to use absolute values because if I have negative, some nth roots won't work. So we want positive terms here. But taking the nth root of a sub n, and then taking the limit as n goes to infinity. This will work really well on certain infinite series. In example 6, we have an infinite series where we have a ratio of n plus 8 divided by 7n minus 3, all raised to the nth power, summed up from n equals 1 to infinity. This infinite series is going to work really well with the root test. The reason why this infinite series is going to work well with the root test is because these terms all are being raised to the nth power. So when I take the limit of those, the nth root of those terms, my a sub n is going to be ratio n plus 8 divided by 7n minus 3, all raised to the nth power. And notice that the nth root and this nth power are going to cancel each other out. So the nth root of the nth power cancels each other out, and I'm just left with the limit of the ratio n plus 8 divided by 7n minus 3, which is the limit of polynomial over polynomial. So it's pretty clear that that limit is 1/7 because both polynomials have the same degree. And I just have to take out the coefficients of the lead terms. So 1/7 is what I get. So this worked really, really nice, precisely because the nth root canceled out with that nth power. Therefore, this series by the root test converges. Now it converges because 1/7 is less than 1. So 1/7 is less than 1. Therefore, this infinite series converges. Now, I want to talk about, again, the way you might see this informally. Well, the way you might see this informally is that the pieces inside that are being raised to the nth power are getting closer and closer and closer to 1/7. So this infinite series is kind of similar to the infinite series where I just take an infinite sum of 1/7 raised to the nth power. This is a geometric series where the base is under 1, and therefore, since base is under 1, this geometric series would converge. Therefore, this series that I have should also converge. So that's really what the root test is doing. And as we can see, the root test we know converges when, again, this is kind of like the R in the geometric series. When the R in the geometric series is less than 1, we converged. When the R in the geometric series was greater than 1 in absolute value, obviously, then we are diverging. And then equal to 1 in the geometric series, it would diverge. But again, here, we're talking about a limit. So this limit might be numbers that are always a little bit bigger than 1 or a little bit under 1. So that's why it's inconclusive when the limit is equal to 1. So that's what the root test is really good at. It's really good at comparing something that kind of looks like a geometric series where R is not just a numerical value, but where R is some expression. And we know that in a geometric series, when the R is less than 1 in absolute value, the series converges. When the R is greater than or equal to 1, it diverges. And so we have this cutoff at 1, and that's kind of the inconclusive zone for the root test. So when equal to 1 is the inconclusive zone for the root test. Less than 1 or greater than 1 is for sure converging or diverging. So knowing that, we can, if you want to skip some of the limit work, you can do that and just say, what kind of R are we talking about here? Let's take a look at this example and do this example. Infinite sum of ratio 2n to the third plus 5, all divided by denominator n to the third plus 2n plus 6. And that entire ratio is being raised to the nth power. You can think about this in light of what we just said and try to determine if this would converge or diverge. So what I would do is I would kind of look inside. This is the informal way. I would look inside and say, what's the limit of this thing that's being raised to the nth power? Well, the limit of this thing that's being raised to the nth power is pretty clearly 2. So this is like having an R of 2 in a geometric series, which is obviously going to diverge. The geometric series would diverge if R is 2. Therefore, this thing, this infinite series, is also going to diverge. Now, that's sort of the informal way of doing it, is just looking at this ratio that's being raised to the nth power. If I wanted to, I could do the formal way as well, where I take absolute value of the a sub n and then take the nth root, take the limit of that as n goes to infinity. But if I take the nth root of absolute value of a sub n, I essentially get my ratio in there, 2n to the third plus 5, all divided by n to the third plus 2n plus 6. Which in fact is 2, which is bigger than 1, therefore the infinite series diverges. So if you want to do it formally, then you go ahead and do the formal calculation of that limit. If you want to just say, oh, that looks like an R of 2, and therefore the infinite series diverges, that's fine as well. Here's another example, example 8. We have 3n squared divided by quantity 4n to the third plus 5n squared minus n plus 6, all raised to the nth power, summed up from n equals 1 to infinity. In this case, you'll notice that the interior function, while it's never a 0, the limit is going to be 0. So in a quick root test, we see that this inside ratio has a limit that's equal to 0. So something like 0 raised to the nth power. Well, that's going to converge. 0 less than 1. Again, this is kind of like having an R equals 0 or R close to 0. Maybe a better term there. So it's like having an R that's really, really close to 0 in my geometric test. And therefore, this infinite series converges. Let me just write that down. Again, if I'm doing this informally, I would say R is approximately 0, or you can even say R is equal to 0 in a geometric series. And in a geometric series, anytime R is less than 1, this converges. If I wanted to do this formally, I take the nth root of the nth term and let the limit as n goes to infinity. The nth root of the nth term, the nth root cancels out the nth power, so we're just left with the ratio there, and the ratio has limit of 0 because higher degree polynomial in the denominator. Since 0 is less than 1, again, like an R of 0 in a geometric series, then this thing converges. So on something like that, the root test is very handy. Again, I don't, in my class, I typically just say, oh yeah, that looks like an R close to 0, and then I don't write out this step formally. But some people, obviously, there are some instructors who would maybe want this step written out formally. I tend not to. Let's take a look at one more example on the root test, where we have this form of ratio raised to an nth power summed up from, let's say, 1 to infinity. Here we have infinite series 6n plus 8 divided by 6n minus 3, all raised to the nth power, summed up from n equals 1 to infinity. Now, in this case, my piece that's being raised to the nth power, the limit of that piece as n goes to infinity is 1. So this is like having an r that is really close to 1 in the geometric series. If I do the formal calculations, the limit of the nth root of a sub n becomes 1. In this case, the root test is inconclusive. So I wouldn't know via the root test whether or not this series converges or diverges. And that's because while R is really, really close to 1, it's kind of like 1. If R is just a little above 1, then this infinite sum is going to grow too fast. If R is a little below 1, if it's always a little bit under 1, then that infinite sum is actually going to converge. In this case, it turns out this ratio here is always a little bit above 1. The plus 8 versus the minus 3 makes this thing always a little bit above 1. And therefore, the infinite series actually diverges. But I don't know that via the root test. The root test says that it's kind of like having an R that's really, really close to 1 in a geometric series. And if we're just slightly above 1, then it diverges. If it's slightly below 1, then it converges. This is saying it's an approximately, it's really close to 1, but it doesn't tell me whether it's close to 1 above it or below it. The root test doesn't. I mean, I can figure that out on my own, but the root test doesn't tell me if it's a little bit above or a little bit below. So the root test is inconclusive on this one. So root test is inconclusive here. And notice that the root test kind of works the best when we're raising some expression to an nth power. That doesn't mean that's the only time I can do this calculation, though. Technically, I can do the root test for a lot of different infinite series. And the same is true with the ratio test. I can apply a ratio test for a lot of different infinite series. It's just that sometimes a root test may work out the best. Other times a ratio test may work out the best. Other times a limit comparison test or an integral test or a geometric test would work out the best. Let's do one. So my point there is that oftentimes you can use the ratio or the root test for some series. One example of that is this one. If I take an infinite sum of n over 4 to the nth power, you can actually use both the ratio and the root test here. I'll do the ratio and root test both formally for this infinite series. So let's start with the root test. In this case, it is not clear what R would be close to in the geometric series because it doesn't have that something raised to the nth power form. We have 4 raised to the nth power, but then we have an n on top. But we could do this. We could take the nth root of the a sub n term That's the nth root of n over 4 raised to the nth power. Now, if you do that, this limit, well, I'll do a copy paste. So what's going to happen is that the nth root of 4 to the n is just going to become a 4. So I can take the nth root of the numerator and the nth root of the denominator. The nth root of the denominator is 4, and it turns out that if you take the nth root of n, I know that's kind of hard to understand the nth root of n, but it turns out it's going to become 1. So we actually get 1/4. So the root test, this is kind of like having an r close to 1/4 in the geometric series. And therefore, via the root test, this infinite series converges. Now that requires us to know that the nth root of n is equal to 1. Obviously, before 2 seconds ago, you might not have known that. If you encounter something like this, one way to figure it out is to graph it. So how would I graph nth root of n? Well, I'd go y equals x to the 1 over x power. The nth root is like 1 over n, right? 1 over nth power. And so the nth root is like a 1 over nth power. So like square root is a 1/2 power, a cube root is a 1/3 power, a fourth root is a 1/4 power, and so on and so forth. You get weird things over here because of the positive negative nature of x. But on the right, when you start plugging in positive numbers, you'll see the bigger and bigger you get, the closer and closer that is to 1. So as you move out to the right forever, you get closer and closer to 1. And this shows you, again, the graph shows you that the limit of that function is 1. So the root test tells me that this infinite series converges. What about the ratio test? Well, the ratio test is a little bit more natural here because we have exponential growth on bottom and an n to the p growth on top. So the faster order of growth is the exponential. That is going to dictate what happens. Since the exponential is a faster growth than n to the p growth, and it's in the denominator, I know that this infinite series has to converge. So the ratio test also showed that it had to converge. If I was going to utilize the ratio test in the formal way, then I'd take this limit. The formal way would be a little bit trickier. The n plus 1 term is n plus 1, 4 to the n plus 1 power. The nth term is just n over 4 to the nth power. I multiply by the reciprocal of the denominator. That would give me 4 to the nth power times n plus 1 divided by 4 to the n plus 1 power times n. And then 4 to the n would cancel out with 4 to the n. You just get 4 to the first power, which is just 4 in the denominator times n. And in the numerator, you'd get n plus 1. So after you canceled out the 4 to the nth power. This limit is obviously 1/4, which is smaller than 1. So we know by the ratio test that this infinite series converges. In this case, we could do both tests. Actually, the limit calculations are probably easier in the ratio test, as long as I know that the limit is as n goes to infinity of nth root of n is 1. Probably easier calculation in the root test, but in the informal way, it's probably much quicker in the informal way if we're doing the ratio test. So either of these tests work in this scenario, and you can just pick which one you want to utilize. Probably in this scenario, I would have picked the ratio test and done it in the informal way and said the fastest order of growth is exponential. It's in the denominator, so the thing converges. And I would have not done the formal limit calculations. So that's probably what I would have done. I tend to just use the root test in those scenarios where I have an expression raised to the nth power. And then I can quickly take an nth root of that and compare it to a geometric series. So with these two tests, we can handle a few more types of infinite series. We can handle a couple of more complicated infinite series. Things like this. This is one we actually calculated, if you noticed. But again, these two tests have the converge option. Technically, it's a converge absolutely option, the diverge option, and the unknown option. So we have to be careful with that unknown option. With the ratio test works as long as my fastest growth around is one of these types, either the exponential, factorial, or n to the n, or something even faster. The ratio test is not going to work if my fastest growth is an n to the p or less, obviously. The root test works really, really well when I have some expression being raised to an nth power. It can be used on other expressions, but not in a super easy way. So the root test kind of works really, really nice when we have an expression raised to the nth power summed up. But again, our convergence is absolute in these tests. We may have divergence and we may have unknown in these ratio and root tests. So that's the end of this section.